is Mrs. Vrobel. So in this section, we are now going to be talking about solubility equilibria. And it's slightly different than what you've been talking about with equilibrium. Typically, when we're in this section, we're talking about ionic solids. And when we look at those ionic solids, they may be insoluble or they might be slightly soluble. And typically, the solvent is water. Now, in order to understand this, this is a reversible reaction, and typically we are looking at a solid which is being dissolved into ions. So notice that we have nickel hydroxide, and on the right hand side we have the ions that can form within that solution. So when we are looking at these kind of equations, we're also looking at what we call solubility. So this is a molar concentration. And when we're talking about molar concentration, we're talking about moles per, talking about moles per liter, or molarity. Now, notice that they are giving us a different example here where we're essentially looking at silver carbonate. And notice that silver carbonate has a very tiny number. It's 10 to the negative 12th. So some of the numbers we've been looking at previously were 10 to the negative 5th, maybe 10 to the negative 7th. These are really tiny numbers. The first step is, once you have your substance, you want to write a chemical equation based on that formula. And they've put the solid on the left. Notice that on the right, when you're looking at the subscripts of each ion, you want to make that a coefficient. So because there are 2 silver in the formula on the left, it becomes the coefficient on the right. The other thing is, you want to pay attention to charges. So notice that we have a positive charge for silver and we have a negative 2 charge for carbonate. By the way, on the home page, I have towards the bottom a practice quiz for polyatomic ions. So if you want to get better at writing those, you might want to try using that quiz. Now, when we set up the solubility product expression, so it's just like equilibrium, but guess what? It only has products. So no longer do we have the reactant. And the reason why is because when you have a solid that is part of the reactant, it does not show up in the overall expression. So expressions have no solids. Okay, so in order to figure out the concentration of the ions, we have to create an ice table. And notice that because we have a solid, it has a big X on it. And they, in this ice table, show the concentration of the product as being 0, because initially it is not dissolved. But with time, it will dissolve, and obviously it will be a very tiny number. Once again, they also show the fact that we have coefficients, and the coefficient becomes part of the expression. And notice that since there was a 2 there, we are essentially adding 2x. And carbonate, because it has a understood 1 there, it's essentially just a positive 1. Okay, so you set it up same way that you did with the equilibrium ice tables. Instead of KEQ, it's just KSP. So they've essentially shown how to set up the equation. And please remember, because there's a coefficient with silver, it essentially gets squared. Now you have to be careful, because whatever's in the brackets or in the parentheses has to be exponentially multiplied. So that 2x becomes 4x squared, and 4x squared times x gives you x. So once you have that, you're going to plug in the actual value that they gave us, which was 6.3 times 10 to the negative 12, and you're going to solve for x. So obviously they took the cubed root of both sides to solve for the 1.1 times 10 to the negative 4th moles. Okay, so I'm going to do 1, and then I'm going to do number 7, so that way you can practice on your own, and I will share the answer key with you guys in a couple days here. Okay, so for number 1, they want us to write the equilibrium expression for calcium sulfate. So the first thing I want to do is I want to write the balanced chemical equation for that. And notice that we have calcium sulfate solid on the left-hand side, and I want to essentially break down calcium sulfate into ions. Now, because there is an understood 1 for each, the coefficient is going to be an understood 1. Now I want to write the equilibrium expression. So I want to say KSP is equal to brackets the concentration of calcium times the concentration of sulfate. Okay, so that is number 1. Now I want to do an ice table using number 7, and it says that actually no, this is not an ice table. This is the KSP. Okay, I scratched that. We're going to do that one. What the hey. All right, so once again, you have to write a balanced chemical equation for this, and this is a solid. So lead, its charge is a 2+, and carbonate ion is 2-. So when I write the KSP for it, I'm going to do concentration of lead 2+ times carbonate ion, which is 2-. Now they tell me that the concentration of the lead 2 is 2.7 times 10 to the negative 7th. So I have to solve for KSP, and I'm going to plug in 2.7 times 10 to the negative 7th molarity. Now I'm assuming, because this is a 1-to-1 relationship, so Pb 2+ is equal to the concentration of CO3 2-. I'm essentially going to square this. And when I do that, sorry, I gotta get my calculator here. So 2.7 to the negative 7th squared is 7.3 times 10 to the negative 14th. And once again, equilibrium expressions have no units. So you can pretty much leave that as a pure number. Okay, I do want to show you how to do an ice table. So I'm going to do number 11 here since it's towards the bottom. So they want to know the equilibrium concentration of Pb2+ and arsenate. So they give us the KSP, which is 4.0 times 10 to the negative 36. So I have to set up a balanced chemical equation first. Sorry guys, my writing's getting a little messy here. Now I have to put a 3 in front of lead because I have a subscript there, and I have to put a 2 in front of arsenate because of its subscript there. So I'm going to do an ice table. Obviously I have a big X there. I have 0 initially. I have plus 3x and plus 2x. And my equilibrium is going to be 3x and 2x. So I'm going to set up my KSP expression, and it's going to be 3x to the third times 2x to the second. So when I set that up, I'm going to say 4.0 times 10 to the negative 36 equals 27x to the third times 4x to the squared. Sorry, I'm doing my calculator here. So 27 times 4 is 108 times x to the fifth. And that's equal to 4.0 times 10 to the negative 36. Okay, so when you use this on your calculator, you're going to have to use the x to the n function. But I'm going to first divide by 108 just to get rid of. So when I do that, I get 3.7 times 10 to the negative 38. And I want to take the fifth root of both sides. And when I do that, I get 3.2, yeah, I'm going to make it 3.3 times 10 to the negative 8th. And the way to check that is to just multiply that to the fifth power, and hopefully get the same number as you did initially. Okay, so what I would like you to do is go back and do 2 through 6, and then 8, 9, and 10, and then I will share the answer key with you.